Hello, welcome to APL 360. My name is Jamie. This video is part of my series on the APL 360 programming language. In this episode, I'm going to be covering the basics of APL 360. APL 360 was completed in November of 1966. It ran on IBM 360 hardware. It's considered quite primitive when compared with modern APLs. For example, all of the arrays in APL 360 are flat, which means that all elements in an array need to have the same type, either all numeric or all character. It's also missing the format and execute functions as well as the scan operator. In 1973, IBM released APL SV as a successor to APL 360. It included shared variables, system variables, and also implemented format, execute, and scan. For the remainder of this video, I'm going to be using the APL 360 User's Manual as a guide. I'm going to switch over to the manual now and just give you a quick overview of it. Manual's not terribly long, and I do recommend that you skim through it or read it if you have the time. I think you'll find it quite enlightening, and it is very well written. So I'm going to skip ahead to page 11, where we will see the familiar APL keyboard layout. So the keyboard layout does not include all of the valid APL symbols. Some of the symbols that are used in APL are combinations of two of the APL keyboard characters. And so we'll demonstrate that a little bit later for a couple of these. This keyboard is also what is being used in the MVT for APL implementation, and as I'm typing on my keyboard, I'm using a map very similar to this that's printed out next to me to help me remember where these keys are located. On page 27, you'll find the list of system commands. Most of these will not really be relevant in a beginning episode like this, but some of them you will have seen if you have read the MVT for APL User's Manual. There's signing on with a right parenthesis in the user number, signing off. There's right paren clear for clearing a workspace. There's instructions for copying a workspace, erasing global objects, loading a workspace, doing right parenthesis FNS to see what functions are currently defined, right paren vars to see variables that are in the workspace that are globally defined, and so on. So just pointing out where this is located for a few of those basic things. And then the language itself starts on page 57. And so you'll find the definition and information about the language begins here. I'm going to skip forward to page 63. This is something that I also have printed out next to me that I find as a useful reference sheet. And these are the APL primitive scalar functions. There is, this table is broken up into two columns. We have the monadic form on the left. So this is using the particular functions here in the middle with one argument. That's how the word monad is being used here. And then on the right-hand side, using these functions in a dyadic form where we're putting one argument to the left and one argument to the right. Let's see, you'll also see the circular functions being defined down here on the lower left. So these are dyadic, even though they are at the bottom of that monadic column. How the circular functions work is they take a number to the left of the circle, and then to determine which particular function that you want to use. And then to the right of the circle is the argument that you want to apply that function to. So if the number to the left, and that number could be here in the middle from 0 through 7, if it's negative, then you get these functions. Most of them are the arc functions on the over here in the left-hand column. And then if that number that represents a is positive, then you get these functions. These are, again, all related to circles. So we've got trig functions, both regular and hyperbolic, and we have the square root of 1 minus the argument, in this case b, 1 minus b squared, again related to the unit circle. We have those functions here as well. Okay, so moving forward to another page of functions on page 94. These are the primitive mixed functions. Most of these will deal with matrices or 2 or larger dimensional arrays. We will see 1 or 2 of these today, but most of these will be saved for future videos. And then I'm going to move ahead to page 115, which is the beginning of Appendix A. And this starts the sample terminal session that I will be using as my main guide for the instruction in this video and in the next video. So I'm going to be working through this up to the point where user functions are going to be defined. And I will save that topic for the next video after this. Okay, so I'm going to move this out of the way and then bring up my terminal window. So I have MVT for APL running, and so here's just the background console of that. It's up and running. I see the MVT for APL console. I've logged into one of the terminals and made it the recording terminal. This is the other terminal that's just logged in as a regular user. So the first thing I'm going to do is we're using APL mainly as a desktop calculator here. I'm going to multiply 3 by 4 and get 12. We can assign that value to a variable with the left arrow. So we'll say x left arrow, or I'll pronounce it as x gets 3 times 4. Does not display what the value of x is here. If we want to see that, we put x on a line by itself and press enter. We see x contains 12. If we want to input negative numbers, we use the negative sign, which is not the same as the minus sign. So I'm going to say y gets negative, and this is shift of the number 2 on my keyboard, and then put in the number 5. So this is not minus. It is the specific symbol that's used in front of a number to make it represent the negative number. It's not used for, taking a number or an array of numbers and negating all of them. That's the regular minus sign. But when it is next to a number like this, that what looks like a minus sign raised up above is the negative sign. We can add x and y together. So here 12 plus a negative 5 is 7. We can put numbers in scientific notation using the exponential form. So if I want to say 144 times 10 to the negative 2 power, we'll use 144e and then put in a minus 2, and that's equivalent to 1.44. We can assign arrays of numbers to variables. So I'll assign to the variable p the array containing the numbers 1, 2, 3, and 4. We just separate each of those individual numbers with a space. We can see what p contains here. When we use these scalar functions on arrays, it will apply the scalar function element-wise. So if we want to add p to itself, we could say p plus p, and we get 1 plus 1, 2 plus 2, and so on. This even works the same with multiplication. So p times p, not p times 4. We can multiply by a scalar. And so you can see that here. I'll do another one of those in a second. I want to do p times p, and then you see we get the squared of those numbers that are contained in p showing up. So if I take p times y, and y, remember, is negative 5, then we see 1 times negative 5, 2 times negative 5, and so on, and those results. Besides numerical arrays, APL has character arrays. This is essentially how we represent what we would consider strings in modern languages, although it is not, there is not a string data type in APL. These are treated as character arrays. So I'm going to set Q to the character array that contains cats. So we denote that with a single quote, which is shift of the letter K. And then, okay, I made a mistake here. Let me show you quickly about fixing mistakes, and then I may do another example of this later. So if I don't want to just press enter and retype the whole thing, I can backspace. But then I need to do a line feed, which is shift X, and continue the correct typing after that, whatever it was that I needed. So now I think Q should contain the character array cats there. If you want to put the single quote as part of your character array, you need to do something like this. I'll just type it, the cats here, but I want cats with an apostrophe S. So I'll do CAT, put in the single quote twice to represent a single quote inside the character array. And then I left out the S. So I'll just press enter, and you can see it did put CAT apostrophe there. And I'll do it correctly here. And remember the S at the end, and then my single quote to close the character array, and then we see cats there. Our variable names don't have to be only single letter names. We can have multi-character names. So I will set the variable YZ to contain 5, and we can put numbers with these names as well. YZ1 is another variable that's different than YZ, and we'll put 5 in there. We can add both of these together, YZ plus YZ1, and we get 10 for that. If I make a mistake typing, let's say I'm going to do 3 plus 4 plus, but I hit the times instead, 5 plus 6. Now you may be tempted, just because of how we normally use input and output on our in our editors these days, we would just backspace and then put in a plus sign here and then press enter, and that we would think that would put the plus sign there, and then we would be able to press enter and do the complete calculation. But in APL that doesn't work. Backspace moves you to that particular point. It doesn't do any erasure at this point. And so when I typed on top of the plus sign, it tried to combine the plus sign, or sorry, when I tried to type on top of the multiplication sign, it tried to combine that with the plus sign into a new character, but there is no APL character that's represented by that combination. So I get an X, which means that it's an unknown character, and if I press enter, I will get a character error at this point because that combination is not recognized. So how do we do this? We backspace and then we do the line feed as I showed up above, 3 plus 4 times 5 plus 6. I backspace to the place that I made the error. I do shift X to get the line feed, and then I continue from there to the end. And then I get the answer that I'm looking for. Now, although I'm not going to be covering any of the functions that we need to have the multi-character input for in this video, let me just show you quickly a couple that are valid. If I do Shift O, I get the circle character, and then I backspace on top of that. I'm going to do Shift P, which is the star, and this is a valid character, and it's used to implement the logarithm function. Another one that's valid is Shift O with the backspace, and then the backslash character. And so we get a symbol that looks like this, and this is used for transpose. So if you do overtype on top of APL characters with ones that are recognized, you will get those symbols showing up. But without any arguments, I'm going to get a syntax error if it doesn't understand what I mean to do with those, but I did not get a character error. Okay, in this next part of the video, I'm going to, continuing on with the terminal session, we're going to look at the order of operations in how APL does calculations. So to start, I'm going to set x to 3 and y to 4. So these just overwrite the values that were previously stored in x and y with new numbers. Then I'm going to multiply the quantity x and y, and to that I'm going to add 4. And we get 16, so 3 times 4 is 12. 12 plus 4 is 16. That's totally expected. I'm going to leave out the parentheses this time and do x times y plus 4. And this time the answer is 24, which is not expected if we're following the normal mathematical precedence rules or order of operations. The way that APL evaluates these expressions is from the right to the left. So if we look over here, the right number is 4. So APL would say 4 plus y. Y is 4. So 4 plus 4 is 8. And then it sees the multiply, and it's going to take the result of that, which is 8, times the value contained in x, which is 3. And it gets 24. So this is something that we have to get used to. And there is also a way of reading these in English. So although the calculation is done from the right to the left, you can read these in a sensible way from left to right. I make mistakes doing this still, but let's see if I can get this right. So we're going to take x and multiply it by the result of adding y plus 4. So if we think about it that way, we're taking 3 times the result of adding 4 plus 4. So there we get the 8. So we get 3 times 8, we get 24. And I think that reading works for that. Okay, let me show you getting an invalid expression. We did see a syntax error up above, but if I forget an operator between two variables, APL doesn't know what I'm trying to do here, and well, we'll get a syntax error. This is different than another error we can get. If I say x and y together, that looks like a variable name, and I press enter, and in this case we get a value error because nothing has been assigned to the variable x, y. Okay, so moving ahead to some more of those scalar functions, we're going to look at the maximum function. So to the left, so I'm going to write this expression and then talk about it. We'll do 4 times 3, and then we're going to put in the upstyle character, which is shift of s, and then 5.1. So we see that the maximum in the middle. And again, based on our normal standard mathematical thinking, we might think that when we press enter, this should produce 12, because on the left of the maximum, we have 4 times 3. We would think that would evaluate to 12, and then we have the maximum, then we see 5.1 on the right. We don't get that at all. So again, we have to think about evaluating this from the right to the left. So we have 5.1 to the right of the operator, and we have a 3 to the left, and ignore the multiplication. We do this part first. So what is the maximum of 3 and 5.1? The maximum there is 5.1, and then the multiplication is done. 5.1 times 4 is 20.4. So if we do mean the maximum of the quantity 4 times 3 and 5.1, we need to put 4 times 3 in parentheses. And then we can do the maximum and 5.1. And then we get 12, as we would expect there. If we use the upstyle character monadically, so I'm going to write something here that's a little bit different. It looks similar, but it's different. We'll see how. 4 times the upstyle of 5.1. Now when you look at the symbol up style here, there is no number immediately to the left, so that means that the up style character is being applied to only one operand here. So this will represent the ceiling function now. So we can read this as 4 times the ceiling of 5.1. And the way that ceiling works is it rounds up to the nearest integer. So we get 4 times 6 in this case, which is 24. I'm going to show you using the index generator function. This is a quick way of generating numerical arrays. So if I want the array of the numbers from 1 through 5, we could assign it this way. X gets 1, 2, 3, 4, 5. But we can also use the iota, which is the index representing the index generator function, to do the same thing. So we'll say X gets, and I do Shift I to get iota of 5, and then I'll display X, and we get 1, 2, 3, 4, 5 for that. Iota of 0 produces a vector, but it's the empty vector, and it displays as a blank line. All of our scalar functions, as I mentioned, they extend to calculations with vectors. So I'm going to assign here y gets 5 minus x. So remember, x is 1, 2, 3, 4, 5. So we get 5 minus 1, and then 5 minus 2, 5 minus 3, and so on. So those numbers become 4, 3, 2, 1, 0. We can take the maximum now of the two vectors. So let's remind ourselves what x contains and what y contains. So there are the two vectors together. Let's think about what we would get if we do the maximum of x and y. So these are going to be compared element-wise. So in that first position, the 4 and the 1 will be compared, and the maximum will be produced. And in the second position, the 3 and the 2, and so on. So the result we get there will be 4, 3, 3, 4, 5. We can use the mathematical comparison operators to do something similar. So we can do x, and then we'll use less than or equal to. So that is shift of the number 4, and then y. So where is x less than or equal to y? This will produce, we'll do a comparison and produce a true or false for each position in those arrays. 1s represent true and 0s represent false. So x is less in positions 1 and 2, but not in 3, 4, and 5. Okay, so now I'm going to move ahead to just do some demonstrations using the circular functions. If we just apply circle to 1, circle represents pi if it's by itself. Here we're multiplying pi by 1, and so we get the numerical value, of course rounded off here, of pi. We can take pi divided by a numerical vector of 1 and 2. So we get pi divided by 1 in the first position and pi divided by 2 in the second position. Next, I'm going to set x to be the angles 45 and 90. And then convert those into radians. So I'm going to do circle of x. I did Shift X and didn't mean to do that, so let me press enter there. I want circle of x. So here we get pi times x, and then we're going to divide by 180. And so we get angles 45 and 90 degrees as radians. The trig functions in APL assume that the angles will be in radians. So if I want to get the sine of a 1 radian angle, refer back to the table of dyadic circle functions on page 63 if you want to see these listed. So the sine function is represented by a positive 1 to the left of the circle, and then on the right is the argument. So the argument here will be a 1 radian angle. So that's a 1. So 1 circle, that unit represents sine. And we get 0.8415. Next, I'm going to take the cosine of the array that contains 1 radian and 2 radians. So the cosine function is specified by 2 circle, and then the array argument after that will just be a 1 and a 2. And we see the results there for the cosine of those. Tangent is 3 circle, and if I want tangent of 1 radian, we can write it that way. Now if you make the argument to the left of circle negative, in most cases you will get the arc version of the trig function. So I'm going to do the arc tangent of 1 radian. So I'll do a negative 3 circle and then 1 representing 1 radian. We see the number there. We can see that tangent and arctangent are inverses of each other if we write this next expression, 3 circle representing tangent and then minus 3 circle representing arctangent, and we'll apply that to the numerical array 1 through 7 using the index generator iota 7. And we get back what we started with, showing that we do get the inverse of the operations there. The fourth circle function is related to the equations of the equation of a unit circle. So I'm going to set y equal to the array 1, 2, and then I'm going to apply 4 circle to y, and this is doing the calculation, the square root of 1 plus y squared. So I get the square root of 1 plus 1 in essence on the left, so there we see the square root of 2, and then on the right we see the square root of 1 plus y squared would be 4, 1 plus that's 5, so we see the square root of 5 on the right. And then there's a different circle function related to the unit circle if we use 0 in front of circle. So here is the number 0, circle, and then we're applying that to the inverse of y. And I haven't shown you how to get the inverse of numbers, but if we just use the division sign monadically, so in this case, there is no number to the left of the divide sign, so it's being used monadically and being applied to numbers on the right, then it takes the inverse of each of those. So we've got the inverse of 1, 2 showing up here, and then that circular function 0 is the square root of 1 minus b squared, or 1 minus the argument squared here. So we see the results there. Hypertangent is 7 circle. So if I want to see the hypertangent of 1, 2, then we get those values there. We want to do the arc hypertangent and the hypertangent together again, just demonstrating these are inverses of each other. I can do negative 7 circle, 7, I meant 7 circle there, let me retype that. I want negative 7 circle, 7 circle applied to the vector 1, 2, and we get 1, 2 as the result there. Okay, so that finishes the first part of the sample session in Appendix A, and then the next part begins define functions, and so I will start there in my next video. So I thank you for watching and look forward to sharing more about programming APL 360 with you in the future.